Okay, so we're going to start off with some review, looking at limits, but then we're very quickly going to add in a new topic, which is called LHospitals Rule. LHospitals Rule is a very helpful way for us to solve limits. So we've done some review with limits already, just to conceptually get a picture of what limit is talking about. So here we have some function f of x, and what we want to do is think about limit as x approaches a of f of x. And what this is really talking about is as x gets close to a, so as our x value is getting close to a on either side, what we're curious is what is our f of x value getting close to? So the limit as x approaches a of f of x essentially is saying what does f of x get close to when x gets close to a. So this is how we opened up calculus, single variable calculus, talking about limits. So some of these problems are pretty straightforward. So let's look at these problems. So first example, we can use what's called direct substitution. So we have this, the limit as x approaches 3 of 2x. Well, we know what that function looks like. It's a linear function. So when x gets close to 3, we want to know what does our function get close to. Well, just by directly substituting in, we can say 2 times 3 equals 6. So my function is getting close to 6. So in other words, the limit as x approaches 3 of 2x equals 6. If we can use direct substitution, do it. However, many of the problems are going to require us to use something else. We're going to need to factor, for example. So in this problem, we're going to need to factor. And the reason that we need to factor is if we tried to use direct substitution and just plug 3 in. So if we just plug 3 in, we get 3 squared minus 9 over 3 minus 3, which is 0 over 0. And we can't divide by 0. However, you guys are clever math students, and we know that we could rewrite this as the limit as x approaches 3 of x plus 3, x minus 3, all over x minus 3. Factoring it, what cancels off? The x minus 3's. And so this equals the limit as x approaches 3 of x plus 3. Now, we can use direct substitution because there won't be a dividing by 0. So this equals 3 plus 3, substituting 3 for the x, which is 6. Just so that you can see a picture of what this initial graph looks like. Essentially, the graph of x squared minus 9 over x minus 3 is just the graph of x plus 3 with a hole when x equals 6. Sorry, when x equals 3. Okay, looking at the next type of limit problem. This is more of a conceptual idea as a reminder to you guys. So there are no numbers here. This is a very general. So if we think about what's going on, that's the function f of x. And we're looking at some point x and another point x plus h. And this is the value f of x. And this is the value f of x plus h. So what this limit up here is actually finding, that's just the slope. So our limit definition of derivative. So this limit equals the derivative of f of x. Okay, so now we're going to get into one of these problems where we actually need to use the rule, L'Hopital's rule. So we have the limit as x approaches 0 of sine x over x. If we use direct substitution, we get sine of 0 over 0, which we can't have. If we use factoring, well, we can't factor this in further, so we're sort of stuck. So we need a new method, and the new method is L'Hopital's. So L'Hopital's rule. Here's the definition of L'Hopital's rule. The following conditions must be met. So the first condition, if the limit as x approaches a of f of x equals 0 is met, and if the limit as x approaches a of g of x equals 0 is met, and if the limit as x approaches a of the derivatives f prime of x over g prime of x exists. So if the following three exist, then the limit as x approaches a of f of x over g of x is the same thing as the limit as x approaches a of f prime of x over g prime of x. That's kind of a bold thing that you're going to have to kind of believe in for now, and we'll work on this enough that you'll totally buy into it. But this gives us a profound ability to do some otherwise impossible limit problems. So let's look at how we can use that on the problem that we're just stuck with. So the limit as x approaches 0 of sine of x over x. Well, we know that our conditions are met. So the limit as x approaches 0 of sine of x equals 0. The limit as x approaches 0 of x equals 0. And if we look at their derivatives, the limit as x approaches 0 of cosine of x, which is the derivative of sine x, over 1, which is the derivative of x, this is going to exist. And it exists because there's nothing in the denominator to make you dividing by 0. So exists, true, true. So therefore, we can rewrite this problem. This is going to equal the limit as x approaches 0 of cosine of x over 1. And now that we're no longer going to be dividing by 0, we can use direct substitution. And this equals cos of 0 over 1, which equals 1. So we were able to find the limit of something using L'Hopital's rule that before we would not have been able to find. And just graphically, if you wanted to put this into your graphic calculator to see what this looks like, sine of x over x, when for values of x very close to 0, looks something like this, where there's a hole at x equals 0. There's a hole here because we can't be dividing by 0, and this hole occurs at the point 0, 1. So let's use L'Hopital's rule. So here's another limit problem. If I were to use direct substitution, I would be dividing by 0. So if I were to plug 1 into this function, I would be dividing 0 over 0. So what I can do is use the derivative. So this equals the limit as x approaches 1 of the derivative of the numerator, 3x squared minus 3, over the derivative of the denominator. So negative 1 plus 3 ln x, 1 over x. Well, we just used L'Hopital's rule. However, if we use direct substitution now, plugging 1 in we're again going to divide by 0 over 0. There's no limit to how many times you can use LHospitals Rule, though, so this equals the limit as x approaches 1. Take the derivative once again. 6x over, well, negative 1 goes away. Derivative of 1 over x is negative 1 times x to the negative 2. Now, we can substitute without having division by 0. If we now substitute x equals 1 into our function, we get 6 over negative 1, which equals negative 6. So what we just found is, as x approaches 1, our function is getting close to negative 6. So we can extend L'Hopital's rule a little bit. So what we showed before is that the limit as x approaches a of f of x over g of x was either 0, if it equaled 0 over 0, then we could look at the derivatives. But we're going to extend it. It also can be used if, when we evaluate the limit, we get infinity over infinity. So, extending this, limit as x approaches a, f of x over g of x equals either 0 over 0 or infinity over infinity, then the limit as x approaches a of f of x over g of x equals the limit as x approaches a of f prime of x over g prime of x. So let's look at an example of this. We're looking at when x goes to infinity. If we were to plug infinity into this, we'd get infinity over infinity. So here's a case where we can use L'Hopital's rule. So let's take derivatives. This equals the limit as x approaches infinity of 4x minus 3 over 6x plus 5. If we were to use direct substitution, again, we get infinity over infinity. So we use L'Hopital's one more time. The limit as x approaches infinity. Take the derivative. 4 over 6. The x's disappear. So now, if I substitute, if I use direct substitution, this is just going to equal 4/6. Last one of these, and it's written a little bit different, but we need to remember that the negative exponent, we can express it as a positive exponent by finding the reciprocal. So this equals the limit as x approaches infinity of x squared over e to the x. If I use direct substitution, plugging in x as infinity, I'd get infinity over infinity. So, L'Hopital's rule, take the derivative. The limit as x approaches infinity of 2x. Well, the derivative of e to the x is just e to the x. Again, if I plugged in infinity, I would get infinity over infinity. So, we derive one more time. The limit as x approaches infinity of 2 over e to the x. Now, if I were to use direct substitution, I would get 2 over e to the infinity, which is 2 over a really, really, really big number. So this is 0. So as x approaches infinity, my function is approaching 0. So take some time to reflect on this. Maybe go back, watch it again, and we'll hit some problems